Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 10 on case control data. In this lecture, we're going to briefly talk about case control methods. We'll talk about an instance where using retrospective case control data and a so-called rare disease assumption, we can estimate prospective odds ratios. And then, because this is kind of a lot focused on the odds ratio, I thought I'd talk a little bit about exact inference for the odds ratio. Okay, so let's talk about retrospective, kind of case reference sampling. And again, this is a deep subject. We're going to scratch the surface of it. So in this case, imagine if we wanted to study lung cancer, and here we had some cases and controls, and we ascertained whether or not they were a smoker. Now there's two ways we could collect it. Well, there's conceptually two ways we could collect this data. One is we could follow a bunch of people up over time. Some of them would smoke and some of them wouldn't. And then we could see who obtained lung cancer. That's very hard to do, right? I mean, I think conceptually you can all see that experiment is basically impossible. A much easier experiment would be to go to hospital records and find a bunch of people that were cases that had lung cancer. Let's say in this case we found 709 of them. And then we also found 709 controls that were at some level comparable. And then we retrospectively determined whether or not they were smokers. Now in this case the 709 is fixed, right? And it's whether or not they were a smoker that we are has the ability to vary. Now I should also say that the most common way to do case control methods would be for every case to try and very closely match a control, so that for every case there's a specific matched control. But in this case we're not doing that. Let's say we had a group of cases, a group of case hospital records, and a group of control hospital records, and or a group of control patients, and we figured out a reasonable strategy for getting control patients. And now these 709 is fixed, so what we wanted to ascertain is who was a smoker and not, and whether or not the cases had a greater proportion of smokers, and to kind of make prospective conclusions from this retrospective data. So just in terms of probability, right, we cannot estimate the probability of being a case given that you were a smoker directly from the data. But we can estimate the probability of being a smoker given that you were a case, right? And so we want to work with that, kind of probability rubric. What is interesting is we can estimate an odds ratio. So the odds ratio that we would want to estimate is the odds of being a case given that you were a smoker relative to the odds of becoming a case relative to being given that you were a non-smoker. Okay, so we want the odds of developing lung cancer given that you smoked compared to the odds of developing lung cancer given that you didn't smoke. Well, it turns out that odds ratio is exactly equal to the odds of being a smoker given that you were a case relative to the odds of being a smoker given that you are a control. So in the bottom one we can estimate, the top one we cannot. So here I just directly go through the calculations. The odds of being a case given that you're a smoker divided by the odds of being a case given that you're a non-smoker, the odds ratio of interest, right? And let me just replace case and not with C and S. A case and non-case with C and C bar, and smoker and non-smoker with S and S bar. And here I just churn through the calculations. You can go through these three steps and make sure that you agree. So here I carry through the calculation, and look, this works out to be the probability of being a case and a smoker times the probability of being a not case and a not smoker divided by the probability of being a case and a non-smoker divided by the probability of being not a case and not a smoker. So it's sort of like the probability cross-product ratio. The probability of caseness and smokerness times the probability of being not case and non-smoker divided by the kind of off-diagonal probabilities. Now, and I say this actually proves the result, and I think it does, because honestly, you can just see that if you were to exchange the words case and smoker up at the top, that nothing changes when we get down to the bottom line here, right? Because probability of C comma S is the same as probability S comma C. So I think you can tell to me that this is exactly equal. Or if you want to be very particular, you can then keep working and get to the other odds ratio. But to me, this proves the result from the previous page. And I would also remind you that these are the probability statements, but we estimate those probability and odds ratios from data. And of course, the sample odds ratio is the cross product ratio n11, n22 divided by n12, n21. And the odds ratio is invariant to transposing the rows in the columns. So our estimator has this kind of invariance property, which we would hope, right? It would be weird if we said that the two odds ratios probabilities were equal, but the sample estimates were not equal depending on which one you were treating as the outcome and which one you were treating as the predictor. So that's nice. By the way, the sample odds ratio is unchanged if a row or a column is multiplied by a constant. And then the last thing, this is what we'll talk about, the odds ratio turns out to be related to the relative risk. So the thing is, if you want odds ratios, we've just kind of demonstrated that the odds ratio works out really well, and you can kind of reverse conditioning a little bit when talking about the odds ratio. But we'll talk about specifically the relative risk, which is what people often want to estimate, and how it relates to the odds ratio. Okay, so the odds ratio is here, right? Probability of a smoker given that you're a case divided by the probability of non-smoker given that you're a case, and so on. You can read this top line. Okay, then we can reverse the odds ratio, right? Using the argument from the other page, right? So now we have probability of case given smoker divided by probability of non-case given smoker divided by probability of case given non-smoker divided by probability of non-case given non-smoker. Okay. Then in the next line, just everything is multiplied out. Denominators are raised up to numerators and so on. And then look at this first term here, probability of case given smoker divided by probability of case given non-smoker. That's the relative risk, right? That's if we want to determine who develops lung cancer comparing who smoked to who didn't smoke. That's the relative risk, the ratio of the two probabilities. And then that's multiplied times these things, but I wanted to refer them with respect to case status, so I just 1 minus each of the probabilities. And what you can see is if this ratio that we're multiplying the relative risk times, if it's about 1, then the odds ratio is approximating the relative risk. Often is the case if these two numbers, 1 minus this number and 1 minus that number, that they're similar enough if in fact the case is very rare. In other words, regardless of whether or not you smoke, the probability that you get this disease, let's say lung cancer, is quite small. If that's the case, this so-called rare disease assumption, if that's true, then this ratio will be about 1, and then the odds ratio will approximate the relative risk. And that's what people often talk about, the rare disease assumption, and they use the retrospectively collected data along with the odds ratio to then approximate the relative risk. It's so common. Often people don't even really talk about what they're doing, they just do it. I think that's so common in the epi literature. It's generally not described in a say American Journal of Epidemiology article or something like that. So now just make the small point that the disease has to be rare among the exposed and the non-exposed, not just rare overall. So here's a simple example. Chuck Rohde reminded me of this at one point. So here we have the exposure, yes or no, disease, yes or no. We have 9, 1, 1, 999. So just from the data, and let's assume that this is just cross-sectional data, so all the margins and everything are estimable. So the probability of disease, the estimated probability of disease, is about 1%. The odds ratio works out to be almost 9,000. The relative risk works out to be about 900. So clearly the odds ratio is not estimating the relative risk. And in this case, like I said, because of the sampling, I'm assuming the two are directly estimable from the data. So in this case, what happens is disease is rare among the exposed. I'm sorry, D is rare overall, right? Let's see, what is it? 10 out of 1,010. But D is not rare among the exposed, right? So among the exposed, you actually had 9 times the number of people having the disease rather than not. So anyway, I think this is if you look at the equation, right, it's clear, that both the P of C given S bar and P of C given S both have to be small in order for the rare diseases assumption to apply, and that's the real criteria. I think this is just a numerical. This is a numerical illustration in a hypothetical circumstances where we can estimate all the probabilities well, and we can show that the two aren't approximately equal to each other. So let's just recap about the odds ratio. So an odds ratio of 1 applies no association. Odds ratio greater than 1 is a positive association. Odds ratio less than 1 is a negative association. For retrospective case control studies, odds ratios can be interpreted prospectively. For diseases that are rare among the cases and controls, the odds ratio approximates the relative risk, and the delta method standard error for the odds ratio is the square root of 1 over the cell counts added up. And just to remind you, that's the standard error for the log odds ratio, not the standard error for the odds ratio. So let's just go through our example. We have our lung cancer cases and controls, smokers, yes or no. We get our odds ratio, it works out to be 3. We get our standard error for the log odds ratio, it works out to be 0.26. If we want a confidence interval, it's log of 3 plus or minus 2 standard errors. We get 0.59 to 1.61. We would compare this interval to whether or not 0 is in that interval. If we exponentiate it, then we would compare whether or not 1 is in the interval. In this case, if we exponentiate it, we get 1.8 to 5.0, so 1 is not in the interval. And our estimated odds of lung cancer for smokers is 3 times that, the odds for non-smokers. Okay, so let's talk about exact inference for the odds ratio. This is the last thing I'll talk about in this lecture. Let's let X be the number of smokers for the cases and Y be the number of smokers for the controls. And remember, in this case, X and Y are the random numbers because we're thinking about case reference sampling. So X and Y are the random numbers. The 709 margins are fixed, and we're going to assume that both of them are, say, binomial. And we want to calculate an exact confidence interval for the odds ratio, not an approximate one. So the square root 1 over the cell counts formula is an approximate one. And I'll show that you have to eliminate a nuisance parameter, and I'll show you how to do that. So let's define the logit function as the log of the odds. So logit p is log p over 1 minus p. That's the logit function. So notice that differences in logits are log odds ratios. So if you logit p1 minus logit p2, that's the log odds ratio for p1 to p2. So as an example, logit p, so let's define the logit of the probability of being a smoker given that you're a case as delta. And by the way, this implies that the probability that you're a smoker given a case is e to the delta over 1 plus e to the delta. So if you invert the logit function, you get that. The logit of the probability of being a smoker given that you're a control, let's call that delta plus theta. So it's a different number, but we're describing it relative to delta. But because we're not constraining theta, it can still be any number. But theta, okay. Then we get probability of being a smoker given a control works out to be e to the delta plus theta divided by 1 plus e to the delta plus theta. In this case, theta works out to be the log odds ratio. Okay, so actually just, of course it's the log odds ratio, because if we subtract the two logits, the delta cancels out and we get theta. So theta is the log odds ratio. And in the way that we've parameterized this, delta, this other parameter, is a so-called nuisance parameter. We don't care about that. What we care about is the log odds ratio, comparing smokers to case status. Okay, so let's keep working on the model here. So here we're going to assume that X is binomial with n1 trials, and then we already stipulated that the probability that the logit is delta, so the probability is e to the delta over 1 plus e to the delta. And then Y is binomial with n2 trials, and success probability e to the delta plus theta divided by 1 plus e to the delta plus theta. So then our probability X is the capital X takes on realized value little x, is going to be this binomial probability, and you can kind of work with it and get to where it's this formula right here, n1 choose x, etc. Then, so this is just carrying this over from the previous slide. This is the probability X takes on realized value little x, and then I'm going to look at the probability Y takes on realized value Z minus X, and you'll hopefully see why in a minute. And that's just plugging directly into the binomial formula, and again I have Z minus X right here instead of a particular value, say little y. Okay, now the probability that x plus y, the random variable x plus y, takes on realized value z is a little bit harder to calculate because x and y are not identically distributed. If they were identically distributed, then x would be the sum of a bunch of Bernoulli trials, y would be a sum of a bunch of Bernoulli trials, so x plus y would be the sum of a bunch of IID Bernoulli trials. So they're still both the sum of a bunch of Bernoulli trials, but not the same. Okay? So here's what we can do. We can factor this into, let's suppose that we decompose z into u and z minus u. U parts going into x and z minus u parts going into y, then that probability would be this product right here. Probably x is u and y is z minus u. And so the probability x plus y takes on the value z is going to be the sum over all the possible values of u. In other words, all the different ways we could allocate some of the elements of z to x, then whatever we can allocate the remaining to y. Okay, so that's a quick little formula you can do. Okay, now we're going to get to the point. So now let's look at the probability x takes on particular value x, given that the sum x plus y takes on particular value z. And I'm just going to plug in these three lines up here, right? So the probability x takes on value x is going to be the probability, this numerator probability right here, probably x equals x, probably y equals z minus x. And so just to elaborate on that point, the probability x takes on value x and x plus y takes on value z is this the and probability. Then given that, because we're stipulating that x is value x, that's the same thing as the probability y takes on value z minus little x, and then we can factor those probabilities into the product. So that's the numerator right here, and then the denominator I'm just plugging directly in the probability x plus y takes on value z. Okay, so then you put it all in. Just, you know, if you can follow the mathematics, hopefully you follow the mathematics. If you can't, if you're having trouble with this, because I realize it's a little bit in depth, then if you plug it all in, you wind up with this formula right here. And again, this is very similar to our development of Fisher's exact test. The only difference is now we haven't assumed the null hypothesis to be true. And so what we have here is it depends on theta, this log odds ratio. Okay? So here, but notice it doesn't depend on delta, right? So we've gotten rid of delta, and that's this idea of conditioning away the nuisance parameter. Here, conditioning on x plus y, it conditions away the nuisance parameter. So, but nonetheless, now we have a distribution for our two variables, because remember, if I know, I don't need to talk about x and y if I've conditioned on x plus y. If I know x, then I know y, given that I know x plus y. Okay, so you can use this distribution to calculate exact hypothesis test for theta equal to theta naught, other than 0. The specific case 0 results in Fisher's exact test, the ordinary hypergeometric distribution. And then you can invert these tests to yield exact confidence intervals for the odds ratio. And that is exactly what R does. If you do Fisher.test, it'll give you a confidence interval for the odds ratio. It is exactly doing this this procedure right here. It's inverting the so-called this distribution here, which is called the non-central hypergeometric distribution. So we're not going to go through any calculations with this, because as you can tell at this point it's gotten rather involved. But I did just want to show everyone where these exact odds ratio calculations come from. They basically come from this formulation of the problem as a non-central hypergeometric distribution. So what I'm hoping you got from today's lecture, though, was a little bit of information about the odds ratio, about some of its more general purpose uses, for example, in case control studies, and then also now to talk about a little bit about where some of the more complex formulas for performing inference on the odds ratio come from.